Hi, hello and welcome to our senior design presentation. Our project is the golf cart conversion. I am Cody Gray.
I'm Kyle Weir.
And our sponsor is Luke Dudley, and our advisor is Mr. Jason Sternhagen. So our motivation is currently there's an abundance of used lithium-ion batteries that are just sitting around. There are also low-cost off-the-shelf electronics as well as solar arrays. There's also a superb charging method of maximum power point tracking. And there's also supercapacitors that could be used in very beneficial ways. Objective and how we plan to achieve said objective. Prolonging the amount of time that a golf cart can go before needing to come back and charge via power supply can save a golf course a lot of money. So reducing the number of lead acid battery powered golf carts with the use of lithium-ion batteries to power the golf carts could help them achieve this. How we plan to do that is implementing that maximum power point tracking to act as our solar charge controller to efficiently charge the lithium-ion battery. This could also include a supercapacitor to act as a buffer/backup supply for unideal conditions. Why maximum power point tracking? Well, this allows for the system to track and extract the maximum power from the panel at a given time. Why lithium-ion batteries? In general, they take a fourth of the time to charge, allow you to use them more by the depth of discharge rates, and typically a brand new lithium-ion battery can last up to 45% longer. Supercapacitors can act as a limited power bank for small amounts of time, which would help keep the system going if the solar panel could not charge efficiently at the time.
So this is our block diagram for our project. We have our solar panel on the top left. This in turn will charge our supercapacitor, and this supercapacitor will pass through into our battery charger, which consists of a DC to DC boost converter, as well as a relay placed in between our supercap and battery charger to disconnect and reconnect to the system to provide power when needed. This boost converter will then output power to charge our lithium battery, as well as supplying supplemental power to the golf cart motor controller. We'll be using a microcontroller to monitor voltages and currents, and in turn we'll be adjusting the output voltage on the DC to DC converter by using a servo. So this is our demo. Currently for our setup, we are utilizing a solar array simulator with the given parameters. Our load is a 24-volt lithium-ion battery, and the video on the left will give a brief once-over of our setup, including all the components being used mentioned in the block diagram. And the video on the right will show the system at work and showing it maintaining maximum power point, as well as showing some of the oscillation that occurs when charging the battery. So for this, we have our solar array simulator going to our supercapacitor bank. This will feed into our relay and then to our boost converter. This will then output to that 24-volt lithium-ion battery. And to be measuring current, we have this ammeter here, as well as an LCD to monitor voltages and position of our servo, with our ADC circuits feeding into our Arduino, which then in turn also will enable and disable our little relay, which will in turn enable this larger relay. So at the start of this, we are currently approaching our maximum power point of our panel. And while that's happening, our voltages on our cap is rising. And currently, since our relay is disconnected, we are not supplying power currently to the battery. But as we approach that maximum power and once we reach it, the Arduino will enable a relay, which will in turn start monitoring the supercapacitor voltage and adjusting the servo position in order to adjust output current being fed to the battery. And once the difference is high enough, then we'll start conducting current to be supplied into the battery. And the rest of this video is just showing the oscillation that occurs as the system will oscillate around the maximum power point of our panel.
All right, so results and possible future improvements. So our steady state oscillation error was 1.6%, which is really good. But our average MPPT efficiency was only about 76%. This could be increased by using a smaller potentiometer to limit incrementing sizes. Then also increasing and decreasing the amount of delay between the cycles could also potentially help us improve our efficiency, as well as changing the hardware to better suit our needs. Thank you, and if there's any questions, feel free to ask.